dot was minus 2x2t. So how do I construct this? We want to get x2 dot t. We put it to the integrator. We get x2t. We multiply x2 with minus 2. We get minus 2x2t. Okay, so this keeps on looping. Okay, so that's how we get this equation. Then what about the output equation? It is x1 plus 2x2. Now, so we take x1 multiplied by 1, x2 we multiply it by 2, and then we add them, and then we get 1. Okay, so which is this. Okay, so we can immediately see that you and I have got the output. Okay, so at a broad system level perspective, a system is an entity to which we provide an input and we get an output, right? Here, what has happened is that we have gone into the details of the system. So this green box is the system dynamics. Okay, the internal dynamics of the system. So you and I have drawn a signal flow diagram to show how x1 dot comes about and how by integrating x1 dot we are able to get x1. Similarly, how x2 dot comes about, and by integrating x2 dot we get x2. All right, so that's the idea here. Now, if you look at the state x1, we immediately observe that due to the fact that it's controllable through the input. Okay, the input u of t is directly influencing x1. That state is said to be a controllable state. Okay, so we are going to formally define it, but then we are going to have an intuitive understanding through this example. Okay, so why is it called controllable? Because by adjusting the value of u, the input u, we can essentially regulate the value of x1, right, to whichever value we want. Okay, so that is why it is called as a controllable state. Okay, so that is point one. Now, if we look at x2, what's happening? X2 is not influenced by u at all, right? It's neither influenced by x1. Is it neither influenced by u? Okay, so x2 is influenced only by itself. Okay, x2 dot is minus 2x2. So consequently, the state x2 is not controllable. Okay, it's uncontrollable. Okay, so I hope it's clear why this came, okay, or how this came. Okay, controllable and not controllable. Okay, so once again, before we go into the definition of controllability, yes, please.
Sir, Aditya here. One doubt, sir. x2 dot of t, it is not influenced by input variable. So in that case, it may be constant, no, sir. Like how it is changed.
Okay. Yeah. 1 minute. So a good point. x2 dot is minus 2x2, but then if you integrate it, you will get x2t to be equal to e power minus 2t x2 0. So you can see that still this exponentially decaying function is a function of time, right? So it's not constant. I hope that answers the query, right?
Yes, clear, sir.
So yeah, in response to a non-zero initial condition x2 0, when we can always certainly have some value, okay, which essentially comes in. Okay, so that's the idea with x2 dot. Okay, so but we can immediately observe that x2 dot neither depends on the input u, nor does it depend on the first state variable x1. Okay, so that is why we say that it's not controllable. Okay, so you and I are not able to take it to any value that we want by adjusting the this one, right? Adjusting the control input. Okay, so that is why we call x1 to be controllable, but x2 dot is not. Okay, so I hope that clarifies. Okay, so we looked at a very specific. Yes.
Just one question here. When you said about this pole zero cancellation, so it doesn't. So it means that whenever there is going to be a same value for the pole and zero, it's definitely going to cancel. That is what it is.
So that is a mathematical
Automatically, yeah.
result there. So, but the consequence is that what is the physical consequence? Okay, so that is why some people will prefer the state space representation. We will lose what is called controllability or observability. Okay, so that is why we are going to define these terms. Okay, and then like we are going to study them. Okay, so we will understand the implications shortly. Okay.
Got it, sir.
Okay. So what is this then notion of controllability? So let us say we consider our standard linear time invariant system. Okay, it could be SISO or MIMO. Okay, x dot equals ax plus bu, y of t equals cx plus du. Okay, now let's say the origin is the equilibrium state. Okay, 0. So let's say we have this phase portrait. Just for the sake of example, you and I are taking a two-dimensional state space. Okay, just so that you and I can easily visualize the graphical evolution. Okay, so let's say we take a non-zero initial state x0. Okay, which is here. The question is, given any arbitrary non-zero initial state x0, can you and I find a control input u of t or input u in a finite time, which will drive it to the equilibrium state? Okay, then the system is said to be controllable. Okay, so this is the definition of control. That is, if we are given this system and let's say the origin is the equilibrium state, the question that we ask ourselves is that are we in a position to find an input u which in a finite time interval of 0 to capital T drive any arbitrary initial state to the equilibrium state. So once again, to what to say, link it to an automotive example. Let's say I want to have a car where I want it to follow a path. Okay, so this is the target path. Okay, but my car is somewhere here, right? So obviously there is an initial error. Okay, both in terms of what to say, the lateral position and also in terms of the heading. Let's say this side desired and side. Okay, so there is a error in lateral position, there is an error in heading. Okay, so let us say these are my state variables. Okay, these errors. The question is x0 is not 0. So initially it is not 0. Okay, what is x0? It is x of t at time t equals 0. Okay, so for the context, we should know what we are referring to. Okay, so consequently, what happens is that if you and I are able to, what to say, find now a control input, in this case, let's say a steering input, which will get me to the track in finite time, which is the equilibrium state, then the system is said to be controlled, okay, or completely controlled, which, as we know, is desirable, right? So as a practical engineer, we want this to happen. Okay? So that is why, like the notion of controllability becomes important for practice, okay? Engineering practice. So once again, let me repeat, from the mathematical visualization or the abstract visualization, let's say we have the standard state space representation. Let us say we have the origin as the equilibrium state, and we have an initial state, like which is what to say, away from the equilibrium state. The question is, can we find an input u which will take the initial state to the equilibrium state in what to say, finite time? Okay, so that's the what to say, notion of complete control. Okay, so now we are not going to get into the mathematics as we discussed. Like in this particular course, we are going to mainly look at like applying these concepts, right? So for control design and so on. Okay. So what is this corresponding criteria? The corresponding criteria is that like like if we have the state space representation of an LTI system, we form something called as a controllability matrix. Okay. So what is this controllability matrix? In the case of a single input, single output system, it is this. So if you recall, the state equation for a single input, single output system is x dot equals AXT plus BUT. Okay, so that's what this is. So what we do is that, like this, let's say this is nth order. That means that the state vector is a nth order vector and the state matrix is an n by n matrix. So what we do is that, like, we essentially form an n by n matrix, which is like this. Okay, in the first column we write the vector B, then we multiply A and B, we write the product, then we multiply A squared with B, and like this we keep on going till we multiply A power n minus 1 with B. Okay, so this becomes an n by n matrix. Okay, so we have n rows and n columns, okay, due to this operation. So now the question is, the system is said to be completely controllable if and only if the rank of this controllability matrix is going to be equal to n. Okay, so that's when it's going to be completely controllable. Okay, so so that is the what to say, criteria for single input, single output system. Similarly, for multi-input, multi-output system, this is the criteria. Okay, so we have the matrix A and the matrix B. We write B, A, B, A squared B all the way till A power n minus 1 B. Okay, and that rank should be n. Okay, so this is how we form the controllability matrix, and then like evaluate like how and when the system realization is completely controllable. Okay, so that is the notion of controllability. Okay, so in the next class we will consider a few examples, and then like we will figure out what does this controllability entail. Okay, so essentially, how do I calculate or how do we evaluate controllability for various cases, and from there, like we will figure out how does one do control design. Okay, so that's something which we will do in the next class. Okay, so to summarize what we have learned in today's session. Okay, so we started, we already know about the state space representation, the notion of an equilibrium state, the notion of stability of an equilibrium state, and so on, right? So having studied all these notions, you and I looked at a particular example where we had a second order system, but when we calculated the transfer function, it resulted in a first order transfer function, and consequently what happened is that, like we interpreted that this is due to what is called as a pole zero cancellation, and that led us to a block diagram representation where we consider the signal flow. Okay, and we saw that we essentially had a situation where the state x1 was essentially going basically going to be influenced by the control input, whereas the state x2 is not influenced by the input u. Okay, and this is a decoupled what to say realization. Okay, so so consequently we see that the state x1 is controllable. That means that we can essentially regulate x1 to whatever value we want, but unfortunately the state x2, right, or I won't say unfortunately, but the state x2 is not controllable. Okay, so that is the notion. Okay, so this is the bottom line as far as controllability is concerned, and we formally define controllability as the notion where we wanted the to find a control input such that like the initial state was driven to the origin, okay, in finite time. Okay, so that is the notion of control. So, and then we also looked at the criteria for control. Okay, so that's something which we okay. So this is where we stop today, and then like we look at corresponding examples, okay, in the next class. So any questions about this content, what we learned today?
Sir, am I audible?
Yes, please.
Sir, this is another question on that pole zero cancellation only. So, pole zero cancellation can typically happen on the LHP alone, or it can typically happen on the RHP as well?
It can happen anywhere. Okay, so this was a specific example. Okay, so wherein the pole zero cancellation happened to be at -2, but that's not necessary. Okay.
Second question is on the controllability aspect. I'm able to see that there was another definition online somewhere when I was just trying to understand this. If the determinant of that matrix is not equal to 0, then also system is called as controllable. So
okay. I will tell you where that comes from. Okay, this is a better criteria.
Yeah.
So that condition is applicable only when you have a square matrix or a for a Pareto system. Okay, so the controllability matrix should be an n by n matrix. So rank being n means determinant is not 0 prime. Okay. So rank being n is the primary condition. Okay, so it's better to learn it this way.
Okay. So it's just another interpretation statement only.
You could essentially infer that the rank is n by calculating the determinant of a square matrix and saying that, look, that is not 0. Okay, so but then I will tell you where the issue will come. Right now, let's say we go for a MIMO system. Okay, so MIMO system, what will happen is that the controllability matrix will be a non-square matrix, right? How do you calculate the determinant of that matrix, right? So I hope now it's clear why I prefer that.
Understood. Yeah. So just another question on the same controllability thing. This matrix we are forming based on B, A, B, which is nothing but it's another transformations of those states, right?
So it is not that we can see. It's essentially there is a derivation to it, Prem. You and I have not gone through it. Okay. So, but then the point is, rather than as a transformation, I would look at it as a result. Okay. So by using the definition, you and I get a criteria. See, it is like this. When we studied stability, right? So in the transfer function representation, right? We learned that for Bibot stability, the criteria was to have all poles in the left-off complex. That is a criteria. Okay, so we constructed something called a pole, and we essentially, figured it out. Similarly, when we look at state space for stability of an equilibrium state, you and I looked at the eigenvalues of the state matrix and figured it out, right? Just like that, here also for controllability, we looked at the controllability matrix, and then we are writing a criteria. Yes, yeah, I hope it's clear.
Yeah, okay, sir. That's it from my side. Yeah.
Right? Any other questions? So, by the way, I think once again, as we agreed, I think the final exam is going to be on May. What is it? May 9th, right?
May 9th,
3 to 5.
3 to 5, sir.
May 9th, Friday, 3 to 5 in the department. Okay, so
Since a long time we have not seen your face, sir, can you switch on the camera if possible, sir, please?
Yeah. So I need to then shift to my desktop.
That'll be fine, sir. That'll be fine, sir.
No, but I need to deactivate tab.
Oh, okay, sir. Okay, sir. So it's a lot of effort that you take, sir. Sorry.
No, it's not lot of effort. But what I'm asking is that, if there are no further questions, I can switch to my desktop, right? But if there are questions, I need to write on my tab. See, if I switch on the camera and my tab, you will see the ceiling. Okay. Yeah.
Oh, sorry, sir.
So, any other questions before you want me to switch on the camera in a desktop?
That's all.
Okay, 1 minute. Right. So, let's see whether this will be fixed. Yeah, of course you will end up seeing, hearing from one screen and seeing from another screen. I hope that's not disconcerting to you, right? So,
No problem, sir.
right? Yeah. So as we discussed, we'll have the final exam 3 to 5 on May 9th. Okay. Yeah. And I think Abhinav updated me that he has given you deadlines for the first project.
Yes, sir. Yes.
Yeah. Second project statement, what we will do is that like after today, we will meet next Tuesday. Okay. So next Tuesday and Wednesday, we'll have theory classes because Monday is a holiday on account of, I think, Ramzan.
Ramzan.
So we will not have a class there. Tuesday and Wednesday, we'll have a class. And April 7th, he will present the next project, second project. Okay.
Yes,
And, I think I need 4 more lectures with you to complete the course. After
Right,
that, he will help you with the project submission so that by April end, you are done with all the project submissions. Okay. And
Sure, sir.
May 9th, you can come in person and then like we can finish off the course. Right.
Right, sir.
Perfect, sir. Yeah.
That is all right. Okay. Any questions? Okay. So I hope tomorrow whoever is presenting are already ready. You know, like that. Best wishes to all of them, right? For the project presentation.
Yes, sir.
Yes. All are in preparation mode, sir.
Okay. Good. So attendance, Arunachal, is everyone present? You know?
Yeah, everyone present, sir.
So I marked everyone is present. So then we meet next Tuesday at 5. Okay.
Sure, sir.
Yeah. All the best. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you so much.
Thank you, sir.